Alright, so the goal of this experiment, right, is to determine the empirical formula of a copper chloride compound. And so before we begin, right, let's talk a little bit, of course, about the empirical formula. So please note, right now, of course, most of you are familiar, of course, with the chemical formula. And now today, of course, we're going to be discussing what? Possible, of course, right, empirical formulas. So the empirical formula, please note, right, it's the simplest whole number ratio in which, of course, well, those elements, of course, exist. And as I discuss this section on empirical formula, I'm going to be very clear. We're going to be talking about ionic compounds, right, versus, of course, covalent molecules. And so, for example, let's just say, of course, I have a compound, and we're going to be referring to this compound, of course, as iron 3 nitride. Now, how do we determine, of course, the chemical formula? Well, we all know what, if iron is +3, nitrogen is in group 5, that charge is what, -3, and so the chemical formula for that compound is going to be what? So initially you might say, oh, Fe is +3, and of course is -3, right? But when we talk about our ionic compounds, do you agree? We always use what? The simplest ratio, and therefore iron 3, of course, nitride is Fe, of course, N. So already, of course, when we talk about, of course, when we look at our ionic compounds, you should recognize, right, that, of course, that chemical formula is always, right, of course, in that, of course, simplest ratio. Not the same, however, if I said to you that my compound was, of course, let's say hydrogen peroxide. So for our covalent compounds, and let's do hydrogen peroxide, the chemical formula for hydrogen peroxide is what? It's H2O2, right? Likewise, the chemical formula for dinitrogen tetroxide is N2O4. And so do you agree that when our compound, of course, is covalent, right, we don't use, of course, what, that simplest whole number ratio. And if I therefore look at the empirical formula for these compounds, right, well, the simplest ratio for what? For hydrogen peroxide would therefore be what? Just HO. In the case, of course, of dinitrogen tetroxide, that, of course, will just be, of course, NO2. And so, I need for you to note that for your ionic compounds, the empirical formula is exactly the same, right, as the chemical formula, but not, of course, for our covalent molecules. Now, here's something that you're very familiar with. We're all familiar with glucose, right? C6H12O6. That is, of course, the chemical formula for that covalent molecule. However, what about the empirical formula? So the simplest ratio, and how do I determine the simplest ratio? I just take what? My lowest value here, and I divide through by 6, and so it becomes, of course, what? CH2, right? O. Alright, so I'm going to erase this, and then move on to our other section. So the goal, right, of our experiment will be to determine the, of course, empirical formula for a copper Cl, of course, compound. So how we're going to be doing this is that you're going to be provided, of course, with a solution of copper, of course, chloride. And so, of course, please note it's a blue solution. And in this experiment, we're actually going to be using what? 25.0, right, milliliters of this solution. And, of course, here on that data sheet, please make this note. If I obtain exactly 25 mLs, of course, of this solution, please recognize, of course, that that is equivalent to a mass, of course, of 2.017 grams of this copper chloride solution. So before we begin this experiment, do you agree? I know the mass, right, of my copper chloride solution. Zinc, of course, is a shiny metal, and so when these two combine, we're going to produce what? A clear colorless solution. So zinc chloride, of course, is a clear colorless solution, and so you should also see what? The deposit, of course, of copper solid. And we all know, right, that copper, right, is this reddish brown, of course, compound. And so during the course of this experiment, we're going to be, of course, looking, of course, at some possible, of course, color changes. So how do we determine the empirical formula? So please note, there are several steps, of course, that's involved. In order for you to determine the empirical formula, right, of a given compound, first step, number one, is that you will need to know the mass of each element. And so what are our elements, of course, in this experiment? Our elements, of course, are what? They're both Cu, right, and Cl. So is that possible? Well, we do know exactly, right, the mass of copper, of course, chloride we're starting with in this experiment. And at the end, do you agree that we will know what? The mass, of course, of copper. So despite differences, are we all in agreement? You should be able to determine, right, the mass of Cl. So from the experiment, you'll obtain, of course, the mass of copper. The mass, of course, of Cl, right, can be determined by means, of course, of just differences. Step number two, once you know the mass of each element, the next step will be for you to do what? To determine the moles, right, of each element. And we can all do that hopefully by now, right, by using, of course, the atomic mass of that element. And now here's usually the challenge. Once you know, of course, the number of moles, how do we determine, of course, the ratio? Right, so the final step will be for you to determine what? The ratio in which, of course, what Cu and Cl, of course, exist. And so how are we going to set that up? And so please note, you're going to record what? The moles of copper, and you're going to compare that to the moles, of course, of what? Cl. And so to determine the ratio, what should you do? Well, you should divide each number of moles, please note, by the least right number of moles. So you're going to divide each, and we've done this in class, right, by the least number of moles. And that will give us, of course, our ratio. Okay? And so whatever you obtain, right, you're going to be reporting that. Okay. So in the course of this experiment, there's a few things that I need for you to also note. Care must be taken when we add, of course, what? Or zinc metal, right, to our solution. We need to make sure that we're avoiding, of course, what? Any splattering. So we're going to carefully, right, using, of course, a device to carefully add, of course, the zinc. We're going to use our tongues to carefully add the zinc to our solution. In addition to that, of course, we're going to make sure, right, that all of our what? Copper chloride solution, that blue color is converted, right, completely reacts to give us, of course, our clear colorless aqueous solution. And then we're going to have our deposit, of course, of what? Of copper. But there's a few issues here. Please recognize, of course, that some of the copper metal is going to adhere to the zinc. So care must be taken to remove that solid copper from, of course, that excess zinc, of course, material. And then the final challenge will be to recover that copper solid, and we also want to make sure that it's completely dry. But there's a challenge. Once we have obtained our copper, please note, it's going to be dried, of course, by heating. However, we need to make sure that we're just gently heating this copper metal. And here is why. Copper will react, of course, with atmospheric oxygen to produce, of course, a black solid, which is copper 2 oxide. So please note, when we're trying to dry our copper, we must be very careful, right, that this reaction does not, of course, occur. So we're going to gently heat, of course, our sample. Ready. So I'm going to be transferring, of course, 25 mLs of my copper chloride solution, right, that blue, of course, solution, to our beaker. And then following that, of course, we're going to be adding, of course, our zinc metal. And so, again, keep in mind, of course, that if I transfer exactly 25 mLs, of course, of this solution, right, then that mass, of course, is equivalent to 2.017 grams. And so to confirm that all of our copper chloride solution was transferred, I'm just going to be rinsing, of course, this graduated, of course, cylinder with approximately 5 mLs of water. That, of course, is making sure, notice, of course, it still appears to be slightly light blue in color, right? So that I know, of course, that there is a small amount, of course, of copper chloride solution still remaining in that, of course, grad cylinder. Okay, now that the transfer is complete, by means, of course, of a spatula, right? So I'm using tongs. I'm going to be transferring, of course, my solid slowly, quite slowly. My goal here is to make sure that I avoid any splattering to, of course, my beaker. You'll also note, right, that that zinc metal was what, a clear colorless solution. But as soon as I add, of course, right, that zinc metal, you can see, of course, the deposit, of course, of copper, that reddish brown copper, right, on, of course, that shiny metal. So it's no longer shiny, but it looks now reddish brown in color. Notice, of course, if you recall, I said what? Copper solutions or what? Or blue in color. I will know when this reaction, of course, is complete. Why? Because zinc 2 chloride, of course, is a clear colorless solution. So you might notice, of course, several color changes. This might go, of course, from blue to somewhat green. It will hopefully get cloudy along the way. And then, of course, at the end, right, the solution should appear to be clear colorless. And to make sure that this reaction is complete, I'm going to be adding, of course, a few drops of HCl. So I'm going to keep on stirring. As this reaction goes, of course, you agree that my zinc is going to be reacting. So the amount of zinc at the end hopefully will decrease. And at the same time, we will, of course, produce our copper metal. You can now see, of course, that that solution is looking fairly cloudy with a tint, of course, of red, reddish brown to that, due, of course, to the presence of our copper metal. And believe it or not, this overall process, honestly just takes a few minutes. In terms, of course, of stoichiometry, I should point out to you, of course, right, that our copper chloride solution is actually, of course, our limiting reagent. And so that zinc metal, of course, will be, of course, in excess. So at the end of this experiment, right, I should have, of course, right, a certain mass, of course, of my unreacted, of course, zinc to report to you. So then I think that the solution no longer appears, right, blue in color. I'm going to go ahead and add a few drops of HCl just to confirm, of course, that this reaction is complete. And so we're using, of course, a 10% solution of HCl. It still looks a little bit blue there when it's settled. And so I'm going to be adding, of course, 10 drops or 5 to 10 drops of HCl. So not completely done, so I'm going to keep on stirring until that blue color goes away. Okay, so I'm going to let that settle for a while. And see, of course, if I see any tint of blue, and I probably still do. So I'll keep on stirring away. Notice, however, right, that the solution now is, of course, looks somewhat reddish brown. Once, of course, I've stirred. Alright, so let's check again to see if all the copper chloride solution has been converted. See if this reaction is complete. And so I think it looks like a clear, colorless solution with, of course, that reddish brown, of course, solid at the bottom. Perfect. So So the next step is going to be quite challenging. My goal now is to remove, of course, right, our zinc metal. I'm going to allow it to also dry so that I can determine the mass of that excess zinc that is remaining. And of course, then the challenge will be for us to then transfer, right, our copper metal to, of course, our pre-weighed, right, evaporating dish. Alrighty, so with the aid, of course, of my tongs, I removed, of course, the zinc metal from our solution. And using, of course, our spatula, right, I removed, of course, right, as much copper as possible. The goal here is to make sure, right, that we remove, of course, all of the copper metal. I'm actually also going to take some time, right, to make sure that this zinc metal, right, because remember that zinc was in excess. We're going to take some time to make sure that the zinc metal, of course, dries completely before weighing. Now, in this final step, right, I have to now recover, right, all of this reddish brown solid, which is, of course, is copper. And so to do so, I'm going to again go back and look at one of the techniques that we talked about, of course, earlier, right, in this term. We're going to go ahead, of course, and just decant the solution. So after settling, I'm going to slowly, right, decant that zinc to chloride solution. The goal here is to avoid transferring, which is going to be a bit of a challenge, any of our copper metal. Okay. Now, once complete, I'm going to then wash, of course, my copper with a small amount of water. So I'm going to add approximately 2 ml of water to my graduated cylinder. Alrighty, so this is what we did before. Another technique that we talked about was washing, right? So we want to make sure that we remove, of course, any residual, of course, HCl or, of course, zinc chloride from our copper. So I'm going to wash this twice. It's going to be done twice with 10 ml, of course, of distilled water. So stir to remove any, of course, HCl or, of course, molecules, right, that's possibly adhering to my copper metal. I'm going to let this settle before, of course, decanting to avoid losing, right, too much of our copper solid. And so I'm going to now go ahead and decant, trying to be as careful as possible to avoid losing too much of our, of course, solid. And we're going to do this twice. Now you can see that that solution is somewhat reddish and brown in color, so we are losing a bit of that solid. I'm going to let it settle for a few minutes. But of course, this is always what some possible, right, source of error. Right, in the decantation process, you can make a note in your lab report that we are losing, right, some of our copper metal. Hopefully that will not impact, of course, our final calculations too much. I think no matter what I do, I think I'm going to be losing a little bit of the solid here. Okay, so I'm going to do this once more. A second 10 ml, of course, of H2O was added to complete this washing process. I'm stirring, and then I'm going to allow it to settle for a few minutes. Now, once this is complete, the next step will be for us to go ahead and transfer, right, our copper to our evaporating dish, which has been pre-weighed. Alrighty. And so with the aid of my spatula, I'm going to be transferring, of course, the solid copper. You can now notice, of course, that it's now reddish brown in color. Right? I'm going to be transferring, of course, our solid copper to our weighing dish. And so please make a note of this. The mass, of course, of our empty crucible is 104.308 grams. So the mass, of course, of my pre-weighed, of course, crucible, right, is 104.308 grams. And so using, of course, our wonderful spatula, I'm going to go ahead and transfer as much of the copper that I can without using water, right, initially. To make sure that I remove all of our copper metal, I'm going to, of course, again, use my wash bottle. So I'm going to add a small amount, of course, of water. I'm going to be adding a small amount of water to my container and transferring as much of that solid as possible to that, of course, evaporating dish. Let me try a little trick here, and let's hope this works. Alrighty, amazing. So I think we transfer all of our solid copper to our evaporating dish. And so again, I'm going to allow this to settle for a few seconds and then do my best to remove as much of the water as possible from, of course, my evaporating dish. There is a small amount, of course, of copper adhering to the spatula, so I just want to make sure that I transfer it also to that dish. So I'm removing, of course, all this excess H2O before I start heating. So now here's going to be our next challenge, right? So my copper, of course, is a reddish brown solid. The goal now is to make sure that we determine what? The exact mass, right, of this solid without heating too vigorously. Why? Because, of course, if this is heated vigorously, what's going to happen is that, well, this reddish brown copper metal will be converted, right, to black copper 2 oxide. So we're going to gently heat. So what I've done, of course, is I'm going to transfer this to my evaporating dish. And please note that I've actually set this, of course, right, so it's heating, but I've set it only to about 2 to make sure, of course, that it's not heating too vigorously. This process will probably take about 10 minutes, right, for this copper to dry completely. And then I will report out to you, of course, the final mass of our copper metal. Alrighty, so now, of course, that the copper is completely dry, right, you should be able to recognize that it's, of course, a reddish brown solid. Initially, of course, when we started this experiment, the mass, of course, of this empty crucible was given to you as 104.308 grams. So I need for you to now realize, of course, that the mass of the crucible and the copper is 105.234 grams. And so just by differences, you should be able, of course, to report, right, the mass of that copper. Now, you also have the mass, right, of the copper chloride solution. And so again, from that information, you can also determine the mass of Cl. Okay, and then finally, right, remember we started off, of course, with our zinc metal. The mass of zinc that we started with, of course, in the first half of this experiment was 1.909 grams. After the reaction is complete, please note the mass, this final mass of zinc, is 0.953 grams. And so when you subtract those two values, You should also be able to report the mass, of course, of zinc that was actually consumed during this experiment.